Imagine standing at the edge of a cliff at night, the world below a scatter of lights, each one a tiny, stubborn fact. You throw a pebble into the dark and watch ripples spread across a black lake. For more than a century, physics has been doing something like that, tossing pebbles of experiment into the unknown and watching the ripples of theory. Two of those ripples, special relativity and general relativity, settled into clear, elegant principles. They read like commandments. For special relativity, it is the principle that the speed of light is the same for all observers, and the laws of physics are identical in every inertial frame. For general relativity, it is the principle that gravity is geometry, or more precisely, the equivalence principle that ties acceleration to gravity. From those simple seeds, the rest grows. Quantum mechanics, by contrast, do not come with that kind of single, universally accepted seed. Instead, it arrives as a powerful mathematical toolkit, wave functions, operators, probabilities, that fits experiment with uncanny precision. But ask a physicist, why that toolkit, and you get a workshop of answers rather than a single proclamation. That absence is not a failure. It has opened a lively search for foundational principles. And among the most compelling proposals are those that put information at the center. Relativity gave us startling rules that reshaped measurements and motion without forcing us to abandon the idea of a world made of things. By contrast, information fundamental principles ask us to swap things for patterns of information, a move that can upend our picture of reality itself. It turns particles and fields into answers to questions. That shift is not a tweak. It's a new lens that can make the universe look less like a stage of objects and more like a web of relations in which meaning and being are braided together. When physicists talk about information, they usually mean something precise and structural, such as correlations, distinguishability, the Shannon measure of uncertainty. A thermostat stores information about temperature. A rock encodes the history of forces that shaped it. These are structural facts, not experiences. Two influential voices pushed the idea that information might be more than bookkeeping. John Wheeler offered the memorable slogan, "It from bit," the idea that all physical entities, the so-called it, such as particles, fields, space-time, might arise from binary yes or no acts of information. Wheeler's worldview is participatory universe. Measurement and the answering of questions are not passive. They are creative acts that help constitute reality. Anton Zeilinger proposed a more concrete operational starting point, which says an elementary system carries one bit of information. That is, the most basic physical system can answer one yes or no question. Zeilinger's principle reframes quantum oddities, complementarity, intrinsic randomness, the limits of simultaneous knowledge as consequences of limited information capacity. If a system can only carry one bit, some properties simply cannot be known together. These are not identical claims, but they share a spirit. Treat information as primary and see how much of quantum mechanics follows. Over the past decades, researchers have formalized this spirit into several reconstructions of quantum theory. Different sets of information theoretic axioms about how much can be known, how information transforms, and how systems compose can reproduce the familiar quantum formalism. That convergence is striking. It suggests information constraints capture something deep about quantum structure, but it also raises fundamental questions. Information about what and whose information is this? Do we need a conscious being to obtain such information? Some people push back here by pointing out a useful distinction. The word information in many quantum reconstructions refers to the mathematically defined Shannon-style concept, a dry, structural measure of correlations and distinguishability. Not the everyday sense of meaning, belief, or experience that we usually tie to consciousness, but that gap is bridgeable. Shannon information only makes sense relative to an observer or a channel that knows what counts as a 0 or a 1, and once you introduce knowledge, an observer's view invite a subjective element into the story. So even if the foundational principle starts with a formal impersonal notion of information, it naturally opens the door to questions about knowing, witnessing, and the lived quality of experience. Or, in another word, consciousness. If information is the bedrock of physics, and if conscious experience is somehow tied to the ultimate meaning of information, then consciousness might be the missing piece that tells us what information is when it is not merely being processed. That thought pushes us into three broad positions about how information and consciousness might relate. Position one, information physicalism. Information physicalism treats information as the ontological primitive and identifies consciousness with particular kinds of information processing. Consciousness, like particles and fields, is an emergent pattern of information processing. Complex arrangements of information give rise to subjective experience. But consciousness itself is not fundamental in the same way as information. One implication for such a position is panpsychism. If information is fundamental, perhaps basic information integration accompanies rudimentary consciousness experiences. In this sense, a rock or even an electron has a certain level of consciousness, albeit significantly lower than what human beings experience. Of note, this is different from panprotopsychism, which says rudimental consciousness, sometimes referred to as protoconscious, are ubiquitous. This type of rudimentary experiential qualities may accompany basic informational events, but it does not treat information as fundamental position two, information dualism. David Chalmers proposed a subtler move, double aspect information. On this view, information, or at least some information, has two aspects, a physical aspect and a phenomenal aspect. Wherever information is physically realized, it might also have an experiential side. This is not the same as saying consciousness reduces to structure. It says structure and experience are two faces of the same underlying informational reality. The challenge for this position is specifying which information has phenomenal character. If every physical information pattern has a phenomenal side, this slide leads toward panpsychism. If only some information has phenomenal character, what selects the special cases? So the dualist needs an extra principle to mark out which information is conscious, and that principle is hard to state without becoming ad hoc. Position three, information as interface. A third possibility treats information as the interface between consciousness and the physical world. Here, consciousness is not identical to information nor merely a second aspect of it. Rather, consciousness is non-physical and interacts with the physical through informational channels. In this picture, information is the language of interaction. This idea can be developed in different ways. One version borrows Wheeler's participatory flavor, and the concept of consciousness collapsing wave function from physicists such as von Neumann and Stapp. If measurement events are informational acts that help constitute physical facts, and if conscious agents participate in measurement, then consciousness could shape which informational outcomes become real without being reducible to those outcomes. The interface view faces the standard objection from decoherence. Biological tissue is warm and noisy. Quantum coherence seems to vanish on timescales far shorter than neural processes. If coherence is destroyed almost instantly, how could consciousness influence quantum outcomes? Proponents reply that decoherence explains why certain bases become preferred, but does not by itself select a single definite outcome. The point where indeterminacy resolves into a definite result, the so-called collapse or selection, remains conceptually open. Consciousness, they argue, could bias that selection even after decoherence has done its work. The mechanism is speculative, and the details are unresolved, but decoherence does not logically rule out an interface. Whatever stance you take, there is a hard physical constraint that cannot be ignored. Landauer's principle. It tells us that erasing information has a thermodynamic cost. What is this principle about? Rolf Landauer showed that erasing one bit of information necessarily dissipates at least k times t time log 2 of energy as heat, where k is Boltzmann's constant and t is temperature. This is not an engineering limitation. It is a thermodynamic law. Information processing has irreducible physical costs. If information were merely abstract, a pattern we impose on matter, there would be no reason for its erasure to generate entropy. Landauer's principle means that the universe keeps accounts in bits. This has two important implications. First, it explains why conscious experience is narrow. Our brains process far more information than we are aware of. Attention selects a tiny fraction. The thermodynamic cost of processing and erasing information places a natural bound on how much the conscious interface can handle. Consciousness is bandwidth limited, not because evolution failed, but because physics imposes a cost. Second, if consciousness interacts with the physical via an informational interface, especially one that might involve quantum indeterminacy, then the interface itself must respect thermodynamic constraints. Any biasing of outcomes or additional informational signaling would consume resources. That makes the interface hypothesis more constrained and, in principle, more testable. It predicts limits on how much conscious influence could be exerted and where it might be detectable. So where does this leave us? Quantum mechanics still lacks a single universally accepted foundational principle like the postulates of relativity. But the information perspective wheelers it from bit, Zelinger's 1 bit per elementary system, and the many rigorous reconstructions that followed, has reshaped how we think about information as the foundation of quantum mechanics, or maybe even the universe. It has also sharpened the question of consciousness. Is experience a kind of information, a second face of it, or something that converses with the physical world through information? These are not merely metaphysical speculations. They suggest concrete constraints and possible empirical signatures. Limits on information bandwidth, thermodynamic costs tied to conscious processing, and the precise role of decoherence in the selection of outcomes. They also remind us of a deeper humility. Our theories are maps, not the territory. They highlight patterns and hide others. If you stand again at that cliff at night, pebble in hand, you might feel the same mixture of awe and curiosity that drives physicists. The ripples we see are patterns of information. Whether those patterns are the whole story or only part of a deeper tapestry, whether consciousness is woven into the fabric or stands at the loom, remains an open question. And that is a beautiful place to be, at the edge of knowledge, tossing pebbles, watching the ripples, and listening for what they might tell us next.